professors, guests, teachers, and students. We are Team 51077. Our topic is two interesting mathematical games. First, I would like to present part of our project, Sudoku. We need to fill in 1 to 9 in each row, column, and 3 times 3 region in the Sudoku. Originally, we would like to find out at least how many numbers should be given so as to give a unique solution. Until now, we know 17 numbers should be given, but we find no way to study it. Also, the number of patterns is too large, which is shown on the screen. It is difficult to conclude all patterns, so we add 3 more constraints to minimize the number of patterns. First, the corresponding small row in each big column should contain 1 to 9. Second, the corresponding small column in each big row should contain 1 to 9. Third, the corresponding box in the whole puzzle should contain 1 to 9. In a Sudoku puzzle, we call the first 3 times 3 region 1, 1 square, 1, 2 square, and so on. We notice some special movements of numbers in one of our modified Sudoku. So we introduce the concept of permutation, because it helps us record the changing of position of numbers from one region to another. Let's look at the example. X moves from box 1 to box 4, from 1, 1 square to 1, 2 square. Y moves from box 4 to box 3, from 1, 1 square to 1, 2 square. And Z moves from box 3 to box 1, from 1, 1 square to 1, 2 square. So we call this permutation 1, 4, 3. Then we can now study the permutation of our modified Sudoku. Suppose we fix the numbers in 1, 1 square. 1 cannot go to the first row and first column. So 1 can only go to 5, 6, 8, and 9. And for 5, it can only go to 1, 3, 7, and 9. However, if 1 go to 3, 1 go to 5, and 5 go to 1, then 1 cannot fill in these boxes, and 5 cannot fill in these boxes. Then 1 and 5 will go to the same box. So we can conclude that no bracket should contain 2 numbers. Since there are totally 9 boxes, and all numbers should appear in brackets. And no bracket should contain 4 numbers too. Otherwise, another bracket must have 2 numbers. For example, this one. And how about 153 and 157? 3 and 7 can't go to other boxes because the bracket will contain 4 numbers, which is rejected. So 3 and 7 must go to 1. However, if 3 go to 1, 2 3s in 1, 1 square and 1, 2 square will appear in the same row. So 153 is rejected. If 7 goes to 1, 2 7 in 1, 1 square and 1, 2 square will appear in the same small column. So 157 is rejected too. So the only choice is 159. And by the same method, we get these 16 patterns. Please notice these 4 permutation. Since 5, 6, and 4 are in the same row, that means the whole row, 1, 2, 3, move to another row, 4, 5, 6. We call these 4 permutations coming from interchanging rows and columns. We let these 6 variables to present these 6 permutations. Since sigma 1 squared equals 195, and the other variables are similar, so we can present all 16 patterns by these 6 variables. Then we can now concern 3 problems. Is the permutation from 1, 1 square to 1, 2 square equals that from 1, 2 square to 1, 3 square? Suppose we use sigma 1 to move A from 1, 1 square to 1, 2 square. And use sigma 1 square from 1, 2 square to 1, 3 square. Since sigma 1 times sigma 1 square equals sigma 1 cube, where sigma 1 cube A equals A. That means the number involved will be repeated in 1, 1 square and 1, 3 square. It is not allowed, so the permutation from 1, 1 square to 1, 2 square must be equal to that from 1, 2 square to 1, 3 square. Then, is the permutations move A to the left differ from move A downwards? Suppose we use sigma 1 to move A from 1, 1 square to 1, 2 square, and from 1, 2 square to 1, 3 square. We can't use sigma 1 or sigma 1 square again, because sigma 1 and sigma 2 have been appeared in 1, 2 square and 1, 3 square. So the permutations to move A to the right and to move A downwards are different. Third, how about the permutation from 1, 1 square to 2, 2 square? We find that if sigma belongs to these two and tau belongs to these two, which come from interchanging rows and columns, then the solution of 2, 2 square equals sigma tau or tau sigma. As they both come from interchanging rows and columns, there is no difference between tau first or sigma first. If sigma belongs to interchanging rows and columns, but tau does not, then the solution of 2, 2 square equals sigma tau, but not tau sigma. That means we need to do the one not from interchanging rows and columns first, and then do the one from interchanging rows and columns. Third, if both sigma and tau do not come from interchanging rows and columns, there is no solution for 2, 2 square. We have checked all the cases after handing the report, and we're sure they are true. To conclude, these four permutations are from interchanging rows and columns, but these are not. From our finding, these two can match these 8, and these 6 can match only these 2. So the total number of possible solutions for our modified Sudoku is 9 factorial times 28, which is far smaller than that of the original Sudoku. Our next job is to eliminate one of our additional constraints so as to make our study more generally. We hope our research will open a new door for others to study Sudoku. Another part of our project is about a game. The player giving the least but not repeated number will win the game. For example, there are 4 players and they give out 1, 1, 2, and 3 respectively. Then player 3 is the winner, since 2 is the least but not repeated number in this game. Our aim is to find out the relationship between the number of players and the best number to give. First, we study the case of 3 players. We let P1, P2, P3 be the probabilities of players to make the choices of 1, 2, or 3 respectively. So P1 plus P2 plus P3 equals 1. Suppose X, Y, and Z are playing the game. For one player, the probability of winning of giving 1 is this, because only when the other 2 players don't give out 1, the player giving 1 will win. The probability of winning of giving 2 is this, because only when the other 2 players both give out 1 or 3, the player giving 2 will win. Similarly, the probability of winning of giving 3 is this. And the probability for 1 to win is shown on the screen. We found that when P is maximum, P2 equals P3, and P1 equals P2 equals P3 equals 1/3. However, if we want to prevent other players to change a better plan to oppose your plan, you need to make sure that the probabilities of victory of choosing 1, 2, or 3 are the same. That means this. After finding P1, P2, and P3, we found that we should give more 1 than 2 and 3, where P1 close to 0.464, and P2 equals P3 close to 0.268. We studied the cases of 4, 5, 6 players, and the results are shown on the screen. For 3 to 6 players, the best number to give is still 1. Our further work is to increase the number of players and find out the meaningful patterns. That's all for our presentation.